So this was the basic architecture that we have. So this is the basic architecture of Rnn. So in this we have input terms x0, x0, x1, x2 and xtx, and output is y at every time step. Okay. So how, first of all, we have to see how activations for this are defined. Sorry. So for first layer we don't have activation, so a0 is generally assigned to 0. We don't have activation, so we generally set it to 0, initialize it to 0. For the second layer, so at second layer there are two calculations going on. That is from, first is from current input and second is from previous input. So in a simple neural network formula we have activations are defined by W x plus b. This is a simple neural network. And in a RNN we have two inputs. First is this current input, plus we have additional term that is coming from the previous layer. So we are also learning the sequence, whatever was in the whatever was the previous term in the sequence. Okay, so over here activations for this RNNs are defined as so G is the activation function, which is generally tan H in the RNNs. Generally we use tan H, and we see why specifically tan H. We can also use ReLU, but both of these are popular for this RNN. So G is the activation function, W is the weight, and A is the activation that is coming from the previous layer. X is current input plus B. So B is basically the bias term. Okay. So the activation at every point is defined with the addition of previous activation plus the current input. So over here we have and for the final layer, which is y over here, y, let's say t y. So this is defined as, for the final layer, this is defined as so at every layer, at every over here at y and y0 and y1, if you want output, this whole scenario is called many to many output, many to many RNNs. There are other types of RNN as well. In this scenario, we are basically, this can be example of we are outputting at every step. We are outputting. This is example of, let's say, language modeling. So we have multiple inputs and multiple outputs. What happens is sometimes we have only one output. For example, in a sentiment analysis, we'll give a positive or negative sentiment as output. So that is many to one. So many inputs are there. Many means we have a text consisting of set of words, and output is sentiment, whether it's a positive or a negative sentiment. So that is example of many to one architecture. So over here we have many to many in this, but at that time we are not generating this y1, this y's, that is the only difference. We are not generating these y's, but rest activation values would remain the same. Okay. Over here, so what are the weights? So in RNNs, weights are shared by each and every layer. So whatever is the weights and biases over here would be the same for for all the layers. For example, these weights would be common over here in this layer. This would be here, and so weights are shared. So sharing means just as in CNNs we shared weights using filter. So over here we shared weights, share weights using the common weights are there for each and every layer. So so after one run of this this whole network, weights are updated, and those weights which are updated, which are these weights would be same for all the layers. Okay. So this way in RNNs there are very less number of parameters as compared to uh, simple neural network. So this is also advantage of RNNs. But the idea in this is because x1 term is dependent upon x naught and x2 term is dependent upon x naught and x1, but it cannot recognize those words which it has not seen in the sequence. It will only recognize those words which it has seen in the sequence. Okay, if it's moving from left to right, so it's only recognizing those words which it has already seen. Okay. So now let us have a look at the weight matrix. So suppose we have x which was of 1000 dimensions and activation was, let's say, 100. um, okay, so okay, so we have, let's say, we have x1. So weight over here would be uh, so two types of weights are so this I'm depicting is over here is this is a, you know, this is activation for a1. It is taking input a naught. This is x1. This is x2. It is taking input activation a1 from here, and it is giving some output y. So uh, and y is calculating over here. This y is calculated using weights from here. There are weights from here, and okay, let's, so suppose it is a 5-word input, 5 terms are there. Okay, so we have 5 activations from previous layers, and we have activations from current input. So okay, w BA, and this was WY comma BY. So this is, it will calculate Y predicted 1, it will calculate Y predicted 2, it will calculate Y predicted 3. So this by calculate by predicted code. So this is outputting, this x is outputting this y, and it is calculating the, it is considering the weights that is defined from for this activation multiplication, and plus for this so it will be, these weights are also shared, and these weights are also shared over here. Okay, so so my final calculation is for this is WAX is coming from here into XT plus BA. Okay, and YT is finally predicting I'm writing this YAA as WY and BY simply. Okay, and this WAA is simply I'm writing is WA. This WAX is over here with each and every X over here. This is WAX. This is also WAX along with X. So there would be WAX. This is X1, this is X2, and so on. Okay. So plus into A plus BY. So what is happening here is this is output Y. Basically, this is a softmax layer, and this for applying this softmax layer. So whatever the output this hidden layer is generating, we are applying the softmax over here, and the softmax function, softmax layer would also be having some activation, and it will also be multiplying some weights with it. So this we call it as WYBY. So this is just like the final layer that we have in the neural network. So this is a softmax layer. Over here we have only WX plus B. So simple, this X is basically the activation that is coming from here. Okay, so this activation calculation that is coming from the previous layer. So this is 80, so this is 80. So this activation is this part. So this part is calculating by every node. This is hidden layer, this whole is hidden layer, this is output layer, and now we have received the output. So from here at this point we will receive some Y, at this point we will receive some Y4, Y3, Y2, Y1, and Y1, Y2, Y3, Y4, and Y5. Okay, and then finally after training this first part, so I hope this training is clear. So first of all, step 1, we give some input x1, x2, x3, x4 at x5. At time step 1, x1 will enter this first node over here, x1 will enter over here, and a naught we have initialized to, let's say, 0, or we can initialize it to some value, and then we will calculate the calculations using this first equation. Using first equation we will calculate the activation for the first hidden layer, and then the calculation are passed to the next hidden layer. So next hidden layer, at next hidden layer, two calculations are done. First calculation is from the previous layer, and second calculation is from the current input. So again, this using this same equation, it will calculate the activation for the next layer, and so on. At the same second time step, at first time step also, so at the second time step, it will also generate parallelly this Y output. So to calculate this Y output, we have applied this softmax layer, and this softmax layer is having weights WY and BY, and using equation 2, we will from the at the softmax layer we will calculate YT. Okay, so Y1 and Y2 and Y3, Y4 and Y5 are calculated parallelly with the when it is moving from left to right, as well as it's returning every output at every time step. So at time step 1 it is returning this, it's learning this, and then at time step 2 it is returning this, as well as it's learning second layer. Okay, so this way it is learning. Now after let's say, okay, after learning this part, so it is giving me predicted y, that is predicted term at first position, predicted term is second position, third and fourth and fifth position. Now the predicted term I have, we also have actual term. So in actual term we have, so in the yesterday's example we have seen that y was 1000. John owns a cat, name entity recognition, John owns a cat, and input was John owns a cat, right? So this is output y and this is x. So this was the basic example. So now we have actual y 1000. So this is the actual y we have, and this is the predicted y we have. Now we can calculate the loss over here. So loss is calculated at every layer, at every output. So first loss is created over here. So formula for this is L L2 will be calculated here, L3 will be calculated here, so L4 will be calculated here. So because this is a sigmoid, so the cost function or the loss at every y we use in this RNNs is L L. So at every term, so this is, let's say this was the term John. So for term John, let's say my predicted output was 0.3 and actual output was 1. So it will give me the error. So error, for using the cost function, we can use this log y log predicted yt minus 1 so this is a formula for logistic regression. We have seen it. We can use the same logistic loss in this RNNs. We are not using root mean square because we have a categorical data. So data is categorical, that is in the form of text. So that is why instead of using the formula for using the cost function same as a linear regression, we are using the cost function which is same as logistic regression. Okay, so this is the cost function that we are using over here. So this is for each and every term. So for first term, for John's output was 1 and 0.3, let's say, so it will use this whole cost function formula and it will calculate. Similarly for second term, let's say for owns, it was returning 0, actual output was 0 and it was returning 0.7 or 0.1, let's say. So we will again calculate the error. So we will calculate loss for each and every term. So John owns a cat. So for all the 4 terms, it will give me some output 0.1, 0. Let's say 0, and actual and predicted. So from actual and predicted, I can calculate the total loss. So total loss is basically the sum of all these losses at every term. So this is for term 1, for term 2, and term 3. Term 4. Okay, so total loss is calculated by summing all these individual losses. So total loss formula for this is equals to sum of all the number of outputs that we have. So ty is the number of outputs, number of terms in the output that we have. So if it is a many to 1, so ty would be 1. If it was many to many, so ty was 4. So for each and every individual loss of individual y, we will sum all these individual losses. Okay. So this is the final formula for uh, calculating the loss of this neural network. Okay. So let's go to again to previous section where we have discussed. So we have individual loss. So we will calculate the logistic loss L1 for first term, L2 for second term, for third, for fourth and fifth, and then at the end what we will do is we will sum all these losses. So we will calculate final L, that is capital L. We will take losses of each and every term and we will sum over here. Now this is the forward propagation. We have generated the loss. So up till now we have forward propagation. Now during the backward propagation, what happens is we are moving in this, actually we are moving in this direction, if you see. So we are moving in this way and this way. Okay. So this is the basic direction. So we are moving from here to left to right, as well as from left to upper, uh, top, top right. Okay. So this is the flow of the forward propagation. Now the opposite would be the flow for the backward propagation. So for backward propagation we will move from here to here, from upward to downward. Okay. So this is the flow for backward propagation, and in this row we have flow this way. So if I'm calculating gradient in for the middle, that is hidden layer, so that would be from right to left. So that is backward propagation starting from this point, and it will go from right to left. And if I'm calculating, I'm updating for the gradients of this weights of y and weights of the output layer, so it will move from this way. Okay. So this is exact opposite of direction of the forward propagation. So this is also called backward propagation in time. Over here, this is back propagation in time, through time. So this means that through time means at every time step. So this was time 4, time 5, t is equals to 5. This was t equals to 3, t equals to 2, uh, 3, 2, 1. So this, everything that is happening in this layer. So this part, this whole part, this is called backward propagation through time. When I'm updating the weights, which weights? So this weights of WAA. When I'm talking about gradients of weights of WAA and BA, so at that time, so this is called backward propagation through time, because at each and every step. So how do we proceed for the backward propagation? First we will calculate the gradients at this t is equals to 5. Then we will calculate the gradient at t equals to 4, at t equals to 2, at t equals to 1, and so on. We will reach to final over here, and then we will calculate the gradient. So what is basically gradient? That is the cost del loss with respect to each and every w and each and every j. So until we get the loss, this value of this final loss with respect to this weights and biases that we are giving as input. Okay. So we will calculate the gradient from moving right to left, and after calculating the gradients, we will update the weights using that our gradient descent algorithm. So we will update weights. So this is the training. So we have trained our network first time. So this process would be repeated for a number of epochs, and this way RNN would learn. Okay. So I hope up till now this thing is clear. How do we forward and backward propagate in this network? So if anyone is having any doubts, you can ask. Okay, so I guess no doubts. So let us see some examples of types of Rnn. So Rnn can be of multiple types. So that is one to one. What we have seen in the previous example was many to many. This is many to many. So here we have only one X and one Y. So this is the example of a simple neural network that we have, feed forward neural network, that we have studied in the first unit. So this is a feed forward neural network. So this is a simple feed forward neural network, or this is also called a vanilla neural network. So this is example of one to one. So we have trained so many uh, images and so many other things on this type of networks simply. And in many to many, so example was name entity recognition, and name entity recognition, and let's say language modeling. So I will explain what is language modeling also. And language modeling is basically what are the chances of occurring a sentence in a text. What are the chances of occurrence of a sentence, occurrence of the whole sentence. Okay. And we can example is machine translation. Machine translation is basically you are entering the in English sentences, and it is returning sentences in some other languages. So in that case we have machine language is translated from one X to other Y. So set of X, that is set of terms, is giving as input, and set of Y's it will give as output. Okay. Another example is many to one. So many to one is sentiment analysis that we have seen. So in this we will use the output, that is final output, which is generated from the final layer. Okay. We have multiple inputs, multiple X's, and this is called many to one. So this is sentiment analysis. Um, Analysis, and we are giving the ratings to text. We give 1 to 5 rating to the whole text or something like that. So assigning ratings, that kind of thing, is many to one. Okay. And then we have many to many. In many to many there can be multiple architectures, like, so we have over here. Okay, so over here, so this is one example. This is the x1, x2, and this is y1, y2. So some of the inputs are getting output, some of them are not. So we are selecting a few of the layers and we are taking output from that. So this is also example of many to one, many to many, sorry, many to many. And then we have so just this is for many to many. We can have also the example of activity recognition over here. So activity recognition, frame by frame activity, basically video activity recognition. So what happens in first frame, we will identify the activity. In second frame, we will identify the activity. In third frame, so first frame of video, second frame of video, third frame of video. So we will identify activity in each and every frames. So that is also an example of many to many, many to many uh, recurrent neural networks. Okay. Another example is simply many to one, in which in which we use the previous output for generating the next output. So example for this is uh, so this was the input. So this is example of one to many. So this is example is sequence generation or maybe music generation. So we have empty set, we give just one value as input, one seed value as input, and it will generate some predicted y, and that predicted y I will give as next input, and it will give me some predicted y, then that predicted y I will give as next input. So sequence generation is also an example of one to many. Okay, so there are multiple types of recurrent neural networks. We can implement each and every one of these. Then we have, suppose I'm taking the examples of, so we have seen the word word wise uh, language modeling. We have seen that John owns a cat, so we can also do this thing character wise. So suppose I want to learn a text that is hello, so I can do this character wise as well. I can give h in my recurrent neural network, and I will expect next word as e, and then I will give e as input, and I can expect next word as l. Then I can give l as input, and I can expect l as output. Okay, so this word wise, we can also learn word wise, we can also learn character wise. Okay, so let us have a look at the example of language modeling. So okay, I have shared a Stanford University video in the group. Check that link. They are explaining about RNNs and so many other examples of CNN models, including the inception networks and other networks. So just check that link. So you will also, I have shared one link in the LMS that is for deep learning videos, and it's a good lecture series. You can also check that out. Okay, so let's see. Let us have example of language or text modeling. Okay, so in this, so first is I have. So modeling is basically what is the probability of occurrence of a text in a sentence. Okay. For example, the sentence is, let's say, hello, how are you? Hello, how are you? So what is the probability that I will get a sentence? Uh, I will get this sentence. So what is the chances that I will get this sentence as output? Okay. So because in speech recognition, what happens is some words are maybe having similar pronunciation. So if I'm saying apple and pear, so apple and pear, and I'm saying apple and pear, so both sound similar. So what are the chances that I will get this as output? So this seems more right and this seems more wrong, and so my model should give me higher probability for this sentence and lower probability for this sentence. So this is language modeling. Is basically we have to identify the probability of occurrence of a sentence as a whole. Okay, so suppose this was a hello, how are you? So first step that I will do is tokenize. We have seen how to do tokenize. So I will keep this as first token. This is second token. This is third token, fourth token, and I will add additional token which is end of sentence. That is EOS. So this is fifth token because I need to add this token because I want to tell the model that now the sentence has finished and next sentence is coming up. Okay, so EOS I will add as a additional token. Now I want to learn this, and my output, this is my input x, and my output for this should be the probability of probability of occurrence of hello, and output for this should be probability of occurrence of how given hello, because it's a sequence. This how depends upon hello. So if how is coming, it should come after hello. Okay, so at over here the probability is occurrence of R given how and hello. Okay, over here similarly and so on. So for fifth word, so for fifth final end of the sentence at this point, so final probability would be PAOS given the probability of hello, how are you? Hello, how are you? So if I multiply all these probabilities, this first one multiply second, third, fourth and fifth. So if I multiply all these four probabilities, I will get the final probability of occurrence of this whole sentence. Okay. So for a simple neural network, how do we build the simple neural network for this model? We just use the similar as name entity recognition, same architecture as name entity recognition that we have seen. So we are giving input as hello, we are giving input as first term. I'm doing word wise uh, uh, I'm not dividing it character wise, I'm learning the model word wise. Okay, so hello, how are and you. So this is my hidden layer. Then we have output layer over here. It will give me some output over here, and then so it will give me final, it will give me a probability of this hello, and this will give me probability of hello how, because this probability is depends upon this how and hello, both of these words. So this will give me this probability of how comma hello, this will give me probability of this, and so on. This will give me probability over here, and then we have end of sentence. So over this, so it will give me probability this. So final probability of sentence is P probability of first y predicted y1, sorry, whatever it's calculating over here. So this would be P hello multiplied by P how given hello multiplied by P hello given, sorry, R. So I hope you can get you have to multiply all these five probabilities and you will get final probability of the whole sentence. So occurrence of a whole sentence. This is called language uh, uh, modeling. This is called language modeling. Then we have a similar application for this is we have seen name entity recognition, we have seen language modeling. Similar concept is sequence generation. So sequence generation is nothing. The only thing that is changed over here is this output. Whatever it's calculating the output over here, it will give as input in the next layer. So output from the previous layer, that is y that is generated from the previous layer is given as input to the next layer. So that is called a sequence generation. So only thing that we are giving input in the sequence generation is the first word, that is first term, that is x1, and that first term is basically seed value, and using that seed value we will generate the whole text, maybe the text, maybe the music. So if you want to generate similar words like suppose you want to generate a few sentences on your you want model to generate few sentences on its own. So first you will train the whole model giving the sentences that you have. Suppose you want to generate something related to Shakespeare's uh, uh, text, similar to something related to Shakespeare text. So you will train your model on the Shakespeare text, and while testing, at the time of the testing, you will give only one word as input and it will generate something on its own. using the weights and biases that were trained, it will use it over here, and it will generate some y first word, and this first word is given as input to the next layer, and it will generate. So it will automatically generate next few words. So it will automatically generate this text, whole text. So first word, second word, up to n words, it will generate automatically. So no need to, you don't need to give multiple inputs as x. So much of the x you don't need to give, you only just need to provide a seed value over here, and rest all it will generate. So this is the concept that is used in music generation, text generation, and so many other applications are there. Okay, so we have seen two applications, as well as we have seen forward and backward propagation. Now in the next lecture, whenever we have, so we are going to see how what are the advantages and disadvantages of RNNs. And advantages we have already discussed, but disadvantages is vanishing and exploding gradient problem. So I'm going to discuss these two in detail in the next class, whenever it is, and then we are going to move towards LSTMs. Okay, so this was it, I guess, for today. So any questions you have, you can ask. Anything that was not clear in forward and backward propagation? Anything that is not clear over here? Okay, fine. So I guess that was it.